We'll continue this derivation. So once we get this difference N1 minus N2, the concentration difference is given by this, where negative sign indicates as we move from one side to other, it goes on decreasing. Delta the length, dN by dx is the concentration gradient. So this we can write on the other side here. Let me, so this, half N1 delta A, this we got it. We are substituting for N1 minus N2, which is equal to minus delta dN by dx. So I'll write on this side minus half. Say already we have delta here in this equation, so one more delta, that is delta square dN by dx, which is equal to minus d, the coefficient of diffusion, dN by dx, the concentration gradient, into T. A gets cancelled, it is because it is same on the both sides, or this we can eliminate. So del square I am writing, it is equal to, say, 2 this D and T, or D, the coefficient of diffusion, D is equal to del square upon, say, 2 T. T is the time interval, okay, and del is the length. This del is known as mean square displacement of a Brownian particle when it moves from Pn to Qn of unit length of this imaginary cylinder. Let us calculate, let us call this as equation 1. And the coefficient of diffusion can be determined on the basis of osmotic pressure. If P1, here P1 is the pressure on one end and the P2 is the pressure of the other end on this imaginary cylinder. If P1, say I'll write here, if P1 and P2 are the osmotic pressures at the end P and Q of the imaginary cylinder, then I can write P1 is equal to, say, using gas laws, you can say N1, K, the Boltzmann's constant, and T, the absolute temperature. Similarly, we can write P2 is equal to N2, the concentration, at the other end K and T. We assume that it is maintained at particular temperature. This imaginary cylinder experiences a force, and that force, we know that pressure at this end, we know the cross-sectional area, so we can write P1 minus P2, the difference in osmotic pressure into A becomes force. Pressure is force per unit area, so that is equal to, say, N1 minus N2 K, T common and A. This is the force exerted or experienced by this imaginary cylinder along its positive axis. Now this force is experienced by the particles contained in the cylinder. The number of particles in the cylinder, imaginary cylinder, are N. The mean concentration here, that is N1 plus N2 into 2 is N. A, the cross-sectional area, into the length, or the number of particles contained in the cylinder. So the force exerting on a single particle, I'll write F dash is equal to, say, N1 minus N2 K, the force exerting on a single particle. This is the force experienced by the imaginary cylinder or the number of particles contained in it. The number of particles are thus divided by N A delta. Well, let me call this as equation number 2. Once I get this, substitute in this equation for N1 minus N2, that is N1 minus N2 is given here. N1 minus N2 is equal to minus delta dN by dx. So this F dash becomes equal to a force exerting on the single particle, that is minus, after simplification I'll write dN by dx. This is kT by N, where F dash is dN by dx delta. This gets delta cancelled. There is no N on this, so N remains as it is here. Let me, F dash is the force acting on the single particle, and this where we can write according to transport phenomena, this is the force due to, say, dragging force called as viscous force. This is viscous force. Viscous force experienced by a single particle here, and according to this kinetic theory of gases, we know this force is equal to 6 pi eta. Say, we have written that A radius into V. Let me use here A, the radius here. Okay, so this will be equal to 6 pi eta, coefficient of viscosity A into V is equal to, that is this kT, I'll write kT by N dN by dx. dN by dx is the gradient. I'll modify this N into V, N into V, N the mean concentration here, not the number of molecules per unit volume, so that is same as the mean concentration, NV, okay, that is equal to, say here, minus KT 6 pi eta into A, I'll write as it is, dN by dx. Let me call this as equation number 3. This NV is the number of molecules moving or particles moving to the right, that is per unit area per second. And this we know, N into V, that is number of molecules per unit volume. Here the number of particles, you can say, that is mean concentration into volume. So the number of particles moving per unit area per second to the right is equal to, according to the definition, this is minus d dN by dx. From the definition of diffusion in transport phenomena. Once I get this as equation number 4, I will pass on to this. Sorry, let me write it here. Fine, that is now. So we got equation number 3 and 4. We got NV is equal to this. Let me equate the equation number 3 and 4. Equating Equating equation 3 and 4. Let us do this. That is minus capital D dn by dx, the gradient, velocity gradient, which is equal to minus kt, I will put it in bracket, kt upon 6 pi eta a dn by dx. Right. So from this gets cancelled here, this gets cancelled. So the D, the coefficient of diffusion, which is equal to Kt upon 6 pi eta into A is the radius. We know the relation between Kt and the gas constant. Here I can write that using RT upon N, that is Kt, into 1 over 6 pi eta, the coefficient of viscosity, into A, the radius. I might have used the symbol here different. There we have used it as a diameter. Here it is radius, you can say. So we got this coefficient of diffusion. Let me call this as equation number 5. From equation 1 and 5, go back and see the equation 1 and 5. Equation 1 we have, that is del square upon 2t, which is equal to d, the coefficient of diffusion. That is, from equation 1 and 5 we have this RT upon N into 1 over 6 pi eta into A. But I can rewrite this, that is for del square displacement, square of the displacement, that is RT upon N into 1 over 3, that is 2 here, 3 pi, say eta A into T. T should go that side into T here. Now, this is for what is called as del square is the mean square displacement of the Brownian particle, and that's what mentioned in our syllabus. There are an expression for the coefficient of square, that is del square, mean square displacement. Now from this expression, let me call this as expression, so this is 5, we have written, and solve for n, the Avogadro number, that is RT upon del square into T divided by 3 pi eta into A. So equation number 6 gives us the Avogadro number. Now the question is, we have written this equation in terms of Avogadro number, and we know the Avogadro number is a fixed number. So if this treatment, what is called as Einstein's theory of Brownian motion, on the basis of kinetic theory of gases, if it is true, if it is correct, then using this expression we should get the value of n, and that work has been done by Perrin, another scientist, and this is determination of Avogadro number by Perrin is the last article. Let's go for this also. Determination of Avogadro number, determination of Avogadro number, by a scientist Perrin, P-E-R-R-I-N. It is mentioned specifically in our syllabus. But, so in earlier theory, that is known as Einstein's theory of Brownian motion, what we got here is mean square displacement. Mean square displacement, that is delta square. I can write this is equal to x bar mean square. Is the mean square displacement of Brownian particle determined from the Einstein's theory, and the mean square displacement of a Brownian particle is determined by the Einstein in time t. Perrin is another person. It is a usual method. Even today, the method is going on. If somebody proposes a theory, people will go for its experimental verification, and that's routine here, and it is running centuries together. So Perrin is a person who has verified this Einstein's theory experimentally. He has determined the value of Avogadro number. When Einstein proposed this theory, during that period also the number was known, called as Avogadro number, and its value. The experimental value of Avogadro number is 6 point. Say what is its value? That is 6.025 into 10 raised to 23, right? That is molecules per gram into mole, or 10 raised to 26 per kg. Okay. That value is known to us if everything is correct in this method, that is theory here. The concept is Brownian motion, and Einstein applied the gas theory, that is kinetic theory of gases, to the Brownian motion. He gave that expression. Perrin has verified it experimentally. What he has done, let's see. Perrin used a high resolving power microscope fitted with an eyepiece scale. We have seen a microscope, but high resolving power microscope, and there is eyepiece. For that eyepiece they have provided a scale. What he has done, I have mentioned the Brownian motion is taking place spontaneously and forever. Perrin has observed in a Brownian particle only one particle at a convenient interval of 30 seconds. I will be watching you, or you will be watching me for 30 minutes during this video. Regular classes say it is for 1 hour. In practicals you are watching us for 4 hours and so on. So that is a time interval. So he concentrated on one Brownian particle for an interval of 30 seconds. Every interval. For one interval of 30 seconds he has observed its motion, whether it is going up or down like that along x and y axis. The Perrin has observed the motion of single particle with convenient interval of 30 seconds. With the help of, he has fixed the camera to the microscope. He plotted the position of the Brownian particle on a graph directly. And this observation looks like this, and right here. So this is graph paper, usual graph paper. We have this squares on it, right? A screen as like in CRO screen here. This is graph paper. So plain graph paper, x-axis, y-axis, there is some scale, there is origin. Here's plotted the movement of, say, of a particle. Right, here started, it is zigzag path. It is this graph plotted by Perrin using camera attached to the microscope, observing the particle for every 30 seconds. He got this graph. A zigzag line was observed by joining the successive path. This is for 30 seconds, this is for 30 seconds. He has calculated the average. Let R be the actual displacement, R be the actual displacement in time t. This displacement varies irregularly, but we know that it's plotted along x and y axis, so x square plus y square is equal to r square. Fine. And the x, y are the components of the displacement. So this is displacement from this to this, it is r, and you can resolve it along x-axis, y-axis. You can write x square plus y square is equal to r square. You can sum these parts. Therefore, summation x square plus summation y square, number of observations, that is equal to summation r square. Once we get this, so x and y are the directions which are equally preferred. So if I write simply x square, summation x square is equal to summation, say, y square is equal to half of, say, observed value r square. So therefore I can write summation, say, x square is equal to n x bar square. That is, n are the number of observations, which is equal to half, say, summation r square. Once I get this x bar square, I can write here x, the mean square displacement, that is equal to 1 divided by 2 n, the number of observation, summation r square. We are finding the r and the summation of r square, the number of observations here. So Perrin has measured this and found this displacement vector, that is displacement for fixed time interval, and then taking this del square is equal to experimental value of displaced mean square displacement here. He found it experimentally, and then he substituted in this relation n is equal to r, the gas constant, T, the temperature is kept constant here, del square. The other parameters are seems to be constant, 3 pi eta into A, where A is the radius, eta is the coefficient of a particular liquid there, R is a gas constant. He determined this, that is del square is equal to x bar square. Later on, he took a row of particles, and row of particles are observed, and he found with the help of microscope, and he found the sum of the diameters. So here it is a diameter, sum of the diameters If determine A the diameter and say del square, other terms are constant, and through his experiment, a simple experiment for us, it looks simpler, but when we do it, it is not that easy also. He determined the diameter of a molecule and then mean square displacement part of a particle experimentally. The other parameters are fixed or constant. He got the Avogadro number value, and using this he got this value 6.82 into 10 raised to 23 molecules, say per gram into mole amount here, and this value of Avogadro number within the experimental limit or experimental error, this is found to be little high compared to the existing value of Avogadro number, which is I have written here, that is say 6.025 into 10 raised to 23 molecules per gram into mole. Thus, this is found to be little higher, but within the experimental error. If we reduce that error, it might be. So, this is in close agreement with this. Therefore, we say here that theory proposed by Einstein underlying found to be satisfactory theory of Brownian motion. Well, students, friends, I have complete 10 hours syllabus on kinetic theory of gases. Today I will upload these videos and the notes related to it. There is a rumor, I don't know, I am not sure, there is a rumor that your first semester, that is odd semester, and the even semesters examination will be conducted by the university, and the mode of examination will be multiple choice. We have heard from the university authorities, it is not yet say announced, but likely to be announced. So we have to prepare in that direction. They have notified in the university notifications that this schedule for the examination for both even and odd semester, they will give sufficient time, say reasonable time to prepare for preparation of the students, or the students will prepare their odd semester papers as well as even semester, and they will conduct the examination. Please note the notification. In that direction also will prepare you. We will guide you. If they conduct objective type, we'll go for it. If they conduct descriptive type, we'll go for it. We have to be ready in either way. Thank you.